Hello everyone, this is Alexei, and today we're gonna talk a little bit about some of the basic utilities of Libra, and specifically its matrix and vector um, components, so some sort of linear algebra and some related techniques and such as eigensolvers and matrix inversion and so on. So basically, let's go to this directory. As you can see, it's empty for now, and this is something I have been doing recently. Well, basically, I'm gonna kind of update the mathematics part of the code, and so now it's more kind of compact and more consistent internally. As you can see, this is gonna be directory with tests. So now we have a bunch of these unit tests for each type of objects. For instance, here we're testing the matrix object, and basically this file shows, I mean, if you just look at this file, and you will see what you can do with the matrix. There's another one to show some other properties of same matrix class, or you can do everything for the complex valued matrices, C matrix class, and so on. And in this file, ceigen, I have added a number of tests for eigenvalue solvers and some matrix inversion utilities and so on. And this is still older examples for vectors, but I'm gonna um, change this part as well. Okay, so today what I want to do is basically to kind of take some of these elements from these tests and just basically show you how you can use these objects and their methods to run your calculations. So here I'm going to make my test.py file. Okay, I save it. Just it's empty. Now before I can use Libra utilities, I would like to import the corresponding modules, and basically that's gonna be we need OS system, not utils. We don't need this, and this siglin linalg will be basically the library that implements all these linear algebra things. And as you can see, I refer to the location of the binaries in build directory, where I can compile the code, and then it is structured in a similar way to the source code. So you have the directory source, and in it a mass, and then in it linalg. So and then in this linalg directory, you'll find the binary called siglinalg. And that's basically your library, right? So once you have it, let's see what you can do. First of all, you can create a matrix, right? So that will be a real valued object. Well, and the simplest thing you can do, show matrix, just print it out. Okay, and then now we are gonna execute this file. So and basically just shows the directory, but doesn't print anything related to matrix, because it's just like empty. It doesn't have anything. Now let's initialize it to be a 2 by 2 matrix, and still we'll print it out. Okay, so now you see it is shown up in the output, and it's initialized with zeros. You can shape your matrix in a way you like, let's say 3 by 2, and then print it out. Here it is. Okay, so it's very simple. Now once you have set up your matrix, you want to populate it with something. And there are several ways to do this. And one way is when you use this method set, and then basically ij will be your indices. First one is for row, and the second one is for column, and the third element will be the element, something that you want to add. Okay, let's say we do set 001. Okay, and then after that we will print this matrix out. So that's what happens. Now you have this 2 by 2 matrix with one of the elements set up to 1, or you can basically use a single index, because all these matrix elements are numbered, such way this element is 1, 2, 3, 4. So you basically count all elements in the first row, so all elements in the second row, and so on. So then basically this element would be number 0, 1, 2, 3. So that will be index 3. So let's do this. Set 3 and to some value, let's say -2. Okay. And then here's what we get. So this is simple thing. Now how do we get the okay, actually, let me show you another way, another thing. So now let's have another matrix. Let's just keep this one here, and simultaneously, I think I'll be showing the elements for complex valued matrices. Okay, let's create C matrix, complex valued matrix, and then here we can still do the same things as we did. Well, maybe. Okay, let me see. Basically, before that, I will add print, just something to separate, and then so here's my complex valued matrix. When it's printed out, you see both real and imaginary components. So you can use the same methods as in a real valued matrix. So that basically sets the real component to what you want. But you can also, use different signature of these functions, and then add another variable here, right? So that will be basically your imaginary component of that number. So now we have added two of those, and we can print it out. So here's what you get. Now you see these imaginary components are set to what you wanted. But in addition to that, you can have it in this way. So 0, 1, for instance, and here you can use just a complex valued number plus, let's say, 9j. Right? J is a Python version for I, mathematics notation. And let's see what happens. Here it is. So now we set up both components. So basically you can see that for complex valued matrix you have a little bit of more flexibility on how to set up the matrix elements. Now let's do the access. How do you access this? How do you retrieve these elements back? So the method is get. It's basically it uses the same signature and returns a number. So now we'll be doing print x get 0, 0, just accessing the element by two indices, or print x get 3, right? So just accessing the element by its index. So here you have 1 and 2 for this and this elements respectively, and the same thing you can do for complex valued matrix, and of course, so let's say get what do we want? Let's say 0, 1, and get, let's say, 3. Okay, so now we print it out, and whoops, that's interesting. I think I missed something. Oh yeah, of course I need to do print, right? Print, and now we can see the output. So the first I output this element, and the second one was this. So this is what we get. Okay, so now we know how to set up matrices, initialize them, and get the elements we want. So now what can we do with these matrices as well? Okay, so actually I'll go back to this example, and so this is basically shown in the constructor sets, and there are different ways of set, get, um, uh, trace, and sum. So we can compute trace of the matrix with this method tr trace, and then we can get a sum. So the sum is a sum of all elements, right? And you can do this for both real valued and complex valued matrices. Let's see what happens. So in the first case, you get your trace is -1. Well, in that case, the sum as well -1. The sum. Oh, wait a second. I think I haven't. Yeah, so here also, of course, I need to change x to y, and see what happens to this element. So the trace will be 1 plus minus 1i, and this thing so give you -1, and this gives you -1/2 I, and in addition to that you get this element, so -1 and 10 gives 9. This and this gives you plus 8.5. Okay, so that's a simple method you have. Okay, now what's next? Show matrix and show matrix into file. So now you can. So we already have seen how you can show these matrices, but you can also show them to a file, a text file. So that will be our matrix X printed into the file X, and the same thing we'll do with matrix y, complex valued matrix into y. Okay, so now I run our calculations, nothing happens here, but then if I go back to the test directory, I have these new files. One is matrix X, right? So here it is, and the second file contains the matrix Y. So, oops, okay, of course, I forgot to change it to Y here. Now, what happens? Here's your matrix Y, a complex valued matrix, and it seems like the time for this section is getting to the end. So next, let me see what we can do. And we can also do this bin dump and bin load. It's basically the same thing as for creating. You can do bin dump x to, let's say, dot, and then we'll just run this example for x. Nothing happens here, but then now you have this dot file, which is binary file, as you can see. Well, I mean, basically you can't read it, and that's what we want, so you can store your matrix in a binary format. Okay, so in the first part we have created this matrix, this file dot dat, and that basically using the function being dump, and now we can use that file to reconstruct another matrix, or to initialize another matrix with the same data as the next. So let's do this. Let's first create matrix Z 2 by 2 and we can show it. Okay, and after that we will load bin load the file we have created before, x.dat, and then we'll show this matrix again, see if anything will change. Okay, so actually let me first add a few things. So print z and print z again, so twice. Okay, so the first one, z is just an empty matrix with all elements set to 0. Now it is the same as our original matrix. Okay, so that's how it works. Here's another, wait a second, so this is assignment and copy constructor. So let's talk about this topic for a little bit. There is another way, of course, to create a matrix. Let's do it the same way. So Z, but you can do it this way. So matrix Z is equal to matrix of X, right? So that will that will create a new copy, a new object totally independent of X, and basically will copy the content of X into Z. So we'll just do it this way. So we don't need those elements. Let me also remove all these things. You already know that. Okay, so that's called copy constructor, and that's a way to create a copy of a matrix if you already have something. Now you might think of, okay, like why would I do this like copy constructor if I can do z is equal to x, so just kind of naive way of assigning. Okay, let's see what happens. So you assign it this way, and then let's print matrix z, and then let's try to change this z, some of the elements of z. We'll set, let's say, 0, 1 to 10, or maybe to 100, okay? And after that, we will also show this matrix z, but let's also show the matrix x. And for now, I'll just comment this part. Let's see what happens. Actually, I'll add some of the printouts. So print z, and print x, right? Now what happens? So here, once we do this assignment, initially z is a copy of x, right? Then we assign this element of z to number 100, and it changes as we expect. But what happens is that the original matrix X is also modified. So this happens because this assignment is done by reference. Basically, Z is just a reference to the existing object X. So when you change something in Z, you automatically change the same things in X. So that's why we don't want to use this assignment operator unless this is what we really want. And by the way, this doesn't necessarily happen on the C++ side. There actually you have the assignment coded in a proper way, but once you expose this to Python, Python doesn't, does everything by references. So that's why unless you code it otherwise. So that's what happens when you do this. But let's see what happens if we use copy constructor. So z is a copy of matrix x, and then we will do the same thing. So we'll just print out z, we'll modify z, and then we'll print out x. And of course, we will remove this part for now. So now this is what happens. This is your copy like z. After you have copied x into it, and then this is z after you have changed one of the elements, and this is x after you have changed z. And you can see that x stays unchanged. This is exactly what we want. So, okay, now we have talked about ways of initializing matrices and using the copy constructor and kind of some sort of warning about this assignment operator. Now, actually, here's another way to create a matrix or complex valued matrix here. So let's do y1 and then C matrix. Now we can use it this way. And so up here we have set up our x and our z, and they are different now. So now we can use this real valued matrices to create a complex valued matrix by using this constructor, which C matrix x and z, and then we'll just print it out, show matrix, and also do print y1. Okay, so whoa, that's interesting. Oh, okay, because it says matrix and C matrix. We cannot do this. Why? Because here we have used y. Should be z, right? We have x and z. These are our real valued matrices. Oops. And here it is. So here's what happens. This is your y, and its real component is set to your original x, and its imaginary component is set to z. So now you have 1 here, minus 1 here, but also 100 here. Okay, that's very convenient. Now we have talked about the operators and construction. So okay, now we can talk about this call row T transpose. So let's go back to our original example, x, and I think I'll remove this part for now. We'll remove this part to kind of clean up my code. So you can do x dot t that will return a matrix that is transposed with respect to original one, and of course our matrix is diagonal, so let's initialize some off diagonal elements. Let's say 0, 1 to something like 25, 5. Show that matrix, and then once you have transposed it, you can show this matrix, right? And then print t xt. So here's your x and here's your transposed, something as you expected, right? Now what if you do it this way? What if you do x transpose and then you show x? This is something different. This is basically yeah, by the way, so maybe before that, let's do this. So once we have transposed x, let's also show our original matrix, just to show you that it doesn't change. So this is our transposed matrix, and this is our original matrix. So original stays the same, and transposed is transposed. If you do it in a different way, so if you transpose and show this operation actually modifies the original matrix X. So this matrix X here will be transposed with respect to the original one. So here's what happens. Yes, of course you cannot do this. So you can just do it in a two operations. So first is you transpose and then you show it. So now this is your X, right, after you have applied the transposition operator. Okay, that's another example. Call and row. You can extract columns and rows from your original matrix. So let's say we want X, and you take column 1, and then you show it again, show matrix. Now here it is. This is your column with index 1, so that is this one. Yeah, similar way you can extract a row. So let's call it C, and then you can extract row. Let's also take the first one, C, no, R, show matrix. And print out. So actually when you print things, they will be printed according to dimensions. This is the column, so with two elements, so it appears as a matrix 2 by 1, and this is a row with two elements, so it appears as a matrix 1 by 2. So we can actually have fun with these matrices. Let me just do some printing, print R, print C. So you can of course multiply matrices C times R, column and row. So what does it give you? C times R, and then on the top of that show matrix. Here it is. So basically, when you multiply column by row, you'll get a matrix 2 by 2 in this case. Then if you multiply it in a reverse order, you multiply row and column, you'll get a number. So it's basically a scalar multiplication of two vectors. And here it is, just basically product of this and this elements, right? So this is what you can do with matrices and elements that you can extract from them. Okay, so we talked about matrix multiplication, some of the extraction operators, and apparently you can do all other arithmetic actions, such as addition. So let's say we can add a number and then show matrix. We can also do this sort of addition, increment, and then show matrix. We can do division or multiplication of any sort. So let's say we will multiply it by this way, and then print the matrix. So let's do printing. Print 1, print 2, maybe just 1, and then print here something. Also, what you can do, you can add to a specific to a specific element. So let's say I'll just increment 0 maybe 10 element by 100. That's what you can do, and then you print the matrix. So let's see what happens. So we started with just this matrix, and then we added 1. When you do this, it basically adds 1 to all elements, as you can see. Then then what did we do? Let me see. Oh, then we incremented. Well, I mean, so okay. This when you do this, you return a new matrix. In which you have incremented all elements by 1, but then this way you don't change x. Now here you do change x, and then you show the changed matrix, and that's why you see exactly the same result here. Now after that we have multiplied the matrix by 3, and that's why we have like 2 goes to 6, and that's what you get. And after that we have incremented the multiplied matrix. I mean, we have incremented one of the elements of the multiplied matrix by 100, so it goes just here. So that's how you can manipulate matrix. And of course you can do division, subtraction, and in the case of complex valued matrices, you can also use complex numbers. So you can multiply by complex number, you can add a complex number or subtract, and so on. So this is pretty much trivial. What I wanted to Okay, what I want to show some other initialization procedures, and also matrix column and rows swapping. So okay, let's maybe just do it here. So at this point we have some matrix, and then maybe we can do swap calls, and of course we have only one, and the columns 0 and 1, and after that let's just print out the new matrix, and after that we can also do a swapping of the rows, and then print the matrix again. So let's just run this example now. So this is the matrix we've got after all those arithmetic operations. Now we have swapped the first and second columns. So these two elements go here, these two elements go here. And then after that we have modified this matrix by swapping its rows. So these elements go here and this here. So everything is correct. But yeah, so that's basically what you want to do with these matrices. And yeah, example 18 here is basically what you can do. You can search for maximal and maximal elements, or the allocations, and so on. So, but it's also pretty much trivial. I'm not be covering this this example here. And of course you can do the matrix multiplications. Well, here we have demonstrated by just some specific case of matrices, columns and rows. Now instead of that, let me go to this other example with which is kind of more advanced. So for that, I guess I'll just remove everything from here. I'll start from scratch, and basically this is my scratch. Make AB. This is my function. So I want to make a matrix 5 by 5 with some elements. So just here. So let's do A is make AB, and then A show matrix. oops. So this is what we generate, and now we want, let's say you want the first column, the second column, and the third column. So you want a 5 by 3 matrix, and just by extracting the odd columns of this matrix. So what do? Now for that we have this utility called pop submatrix. So this pop submatrix takes two or one. Well, okay. So first of all, it takes the original matrix A. It takes then some submatrix that you want to create. So in our case, it will be 5 by 3 matrix. So let's create it this way. It will be matrix 5 by 3, and this is our stencil, basically kind of the template of for the extraction of elements. So like I said, we want to get all elements from each from certain rows. That means we'll set stencil 1 to the range of let's say this will be just range from 0 to 5, and then we can create another one, stencil 2, which will be just enumerated 0 well, I mean 0 1 2 and then 3 4. Okay, this is what we want. Stencil 1 and stencil 2, they basically define the indices of rows and the indices of columns, on intersection of which we will take the elements and extract them. So basically the intersection of this set and this set defines the elements of the submatrix that we want to extract from a bigger matrix. So this may be very useful at certain points. So show matrix, and now let's see what happens. So this is, as you can see, this is our new matrix, and it contains the first column here. Then we skip the next one, get the third column here, and get the last one here. So let's say we also want not all elements of the columns, but also even or odd, depending on how you counted. So the first element and the -4 and so on. So that basically would mean we will just use the same stencil as here twice to define the indices of rows, right? This one will define indices of rows, and to define the indices of columns. Now, of course, this matrix will be 3 by 3, and that's why we'll have to change it there. Print. This is just for my convenience, and here it is. So now we have these elements that are at the intersection of the columns 0, 2, and 4, and rows 0, 2, and 4. Right. So this is what you get. Now you can take this matrix and you can also put it into another bigger matrix. So let's say we have another matrix B of the size let's say 5 by 5 again. We can print B, show matrix, and then after that we can use this other function called pop submatrix. Not the pop. Now it will be push submatrix, First will be the target, the matrix B, and then the matrix that we want to push will be 3 by 3 matrix A that we have generated here. And if we can use the same stencils as before, so 0, 2, and 4 basically will be the same element as in A, but all other elements will be set to 0. And then after that we of course want to print the resultant matrix, right? So this is our original matrix B, and this will be the B with these elements, inserted to where they have been in the matrix A. But you can of course insert them in a different places in different places. So let's just create this sub block 0, 1 and 2, so 0, 1 and 2, and see what happens now. Now we have these elements in this sub block here. So it's very convenient, especially if you doing some sort of subsystem calculations, and let's say you deal with a density matrix for the overall system. You want to extract the density for your subsystem, or merge these things back to a bigger matrix. This would be very useful. Okay, so this one just demonstrate everything for the complex valued matrices. A few other things that you have here and that you don't have in the real value are the conjugate, complex conjugate, and this Hermitian conjugate. Basically the same stuff. I mean, pretty straightforward. Something I haven't talked about are this initialization and diagonalization. The initialization of diagonal matrices, but that's also pretty much straightforward. Okay, so let's continue with the last part for today, which will be about the solving the eigenvalue problem and related things. So of course, we don't implement everything from the scratch. Libra actually wraps the methods that some of the methods that exist in the eigen package, which is very efficient implementation of this linear algebra algorithms. But then just for convenience, we wrap it and expose it to Python in different forms. So first thing, like kind of related to this is computing determinant. So let's just create this. Okay, this is from the previous example. I'll just erase this, and here is my matrix. Yeah, so just 2 by 2 matrix, and apparently you can. It's not difficult to compute a determinant for that matrix, but of course you when it gets bigger, the computation of determinant in a straightforward way will be more and more computationally expensive. So that's why it's important to use these methods that supplied by the Libra. So you can do this in this way: determinant of age, just real valued matrix. You can create a complex valued matrix, C matrix of the original one, and then you can create compute the determinant of that one. But sometimes I think this determinant is based on one of the methods. Another one is through the so-called full pivot of with LU decomposition, and that's an alternative way of computing determinant. If the first one doesn't work, you can likewise you can apply it to the real valued matrix or the complex valued matrix. Now let's see how that works. Okay, not defined. Okay, why not? Because for this utilities, we have to go to another library, not just the siglinalg, but also meigen. So we will add this into the path, and then we also will import it from sig meigen. Import everything, and now it should work. So here it prints the determinant computed with two ways, for the real matrix and for the complex matrix, and in the latter case it of course returns the complex valued result. Now what can you do else? Let's look at this one. So now of course we want to solve the eigenvalue problem, and here we again start with two matrices, because now, oops, I know what happens. Let me just do it again. I'll copy this. Actually, I can copy this in this way. Just a block. Okay, so this is my matrix 2 by 2. Here's another matrix, and I convert these two matrices to the complex matrices. I create two complex matrices that will contain the eigenvalues and eigenvectors, and then I call this function solve eigen, which basically solves this sort of generalized eigenvalue problem. And then on the left hand side I will have h times c. On the right hand side it's c times c s times c e, and and then basically I can print these two sides. So left hand side, let's do print LHC LHS, let's show matrix. That will be of course a complex valued matrix, and then likewise you can do for the right hand side, and here. And down here I also check that the eigenvalues are eigenvectors are the orthonormal with respect to this overlap matrix. So this is supposed to be true, and then let's just do print CSC, which should be the identity. So CSC show matrix. Okay, now let's try it, and that's what we get. We get left hand side is equal to this, right hand side is equal to this. Both of them are real valued, and I mean they are of course represented in a complex valued format, but they are real valued because our original matrices were real valued. And then this is our identity matrix. Well, I mean a little bit of numerical errors here, but overall it still works pretty well. Now you can also do it. Let's actually print out the eigenvalues and eigenvectors. Print E. Actually, I can do it this way. Show matrix, and I can do this for C. Just curious what they are. Right, so this is my eigenvalues matrix, which is diagonal as we expect, and this is the matrix with eigenvectors. They are both real valued. Now, so if you look into, let me go to the source and eigen, you will see that there are actually several versions of this solve eigen function that I implemented. And of course, this this function that take pointer as an argument, they're only for C++. For Python, we only look at this variants, but they can be like all matrices are real value, just matrix, or we can have input matrices are real valued, the output matrices complex valued, or the variant where everything is complex valued. And now we basically will do a little bit some other examples we find with the eigenvalues. But let's say we want to invert the matrix or compute the square root of the matrix. So that's basically what we are going to do now. And let's go just to our tests. Yeah, so this is basically how you do this. Let's say we want to compute the inverted one and all this half s to the minus 1/2 and s to 1/2. So we'll just create this C matrices. In this case, n is equal to 2. And then I go to this example. So here I have these two functions, square root matrix and inverse matrix. So basically once I call them, the first one will will diagonalize, we'll compute the square root of the matrix S and its inverse, and the second one will just compute an inverse of that matrix. So, and of course the matrix has to be C matrix. Then basically how do we check that everything is fine? Well, of course, we'll need to compute all these products, right, so they are here, and then we'll just basically need to LHS1 show matrix and just do this for several times. And 2, 3, 4, no, 5 is done. And basically just let me run it. Inverse is not defined, and I think I do not have. Okay, let's do it this way. Yeah, so you can see what the input produces. The last two kind of 2x2 blocks are the matrices that's supposed to be 1, because this is like inverse of the S matrix times, or inverse of the S to the minus to 1/2 times it's the matrix itself, and just in different orders, so it has to be 1. This matrix half by half, so there should be also S, well, this is basically the original matrix S, right? So that was something that we okay, let's just print the S matrix. So S show matrix, that's something we have started with, right? So it just will be printed out twice. So this is matrix and 1/2 and 1/2, and this is just basically what let's see, this is an inverse matrix, half inverse, half inverse. So basically if you print the S in inverse and then show matrix, then these two will be the same, and let's check it. Yes, this is just normal inverse. This is inverse computed as a product of two square roots of inverse. So that's how it works. Now, what else do we have? So we talked about this. You can also use these functions to Well, there is this thing called a full pivot LU run convertible. Let's see how that works. It's basically I guess before trying to invert a matrix or compute this sort of things, you can call this function, and then basically this it will return this info, which is a list print info. It will contain two elements. The first one is the rank of the matrix, and the second one is the flag that tells whether the matrix is invertible or not. So let's do this. So info is equal to, and then here let's just start with a normal case when everything should work. So then we see this 2 and 1. 2 is the rank of our matrix 2 by 2, which is what we expect, and 1 means it is invertible. But then let's say we'll do some sort of kind of degenerate matrix, right? When something like that happens, right? And then let's see what happens then. This info tells you that the rank of the matrix is 1, and the 0 means it's not invertible. But then you can still, try computing those things, but not necessarily that they will work out. So let's say, so the first one is what we think is half invertible, so this to first is just inverse of the matrix, and this is of course, well, I mean the matrix is different one, so we should basically look at the product. I think this thing, so whatever we compute, whether it makes sense or not, but this product, this should be 1, this should be 1, and half and half should give you the original matrix. So in the bottom we should have two unity matrices, which kind of works in this case. It does work in this case. Not necessarily it will work in all cases. So you should be careful. Now this is S matrix, and this is a product of half matrix and like square roots of the matrix. They should both be the same. And then we have, this is our original matrix, and this is the one that we reconstruct from the halves. And as you can see, it just doesn't work this way here, because like, okay, maybe for the first column it does work, but here you should have half and half, but you have 1 and half. So then, like, I mean, this result not necessarily is consistent with with the idea that you might have the inverse matrix. So should be careful when you get the non-invertible property. So okay, now what else do we have? And I think one more example will be about the solving the linear systems of equations. And here's just basically an example from this test. So I will copy it, and I think I'll just remove all this stuff and paste it here. So okay, now we have this problem. We want to solve the linear system of linear equations, c times x is equal to d, where we look for x, and now c is a square matrix, but D and X could be like some rectangular matrices. Like in one case, let's say X is just the vector that you want to compute, and then in this case M will be just 1. So D and X are just the vertical vectors, and C will be just a matrix, a square matrix of the coefficients. And here we use, we create the random matrix of coefficients, and we can maybe print it out, show matrix, and then we also generate a random vector of y. Let's maybe call it y, right? So that will be like x and y, and that will be just y here. So we can show it matrix without triple R. So this is y, print, and this will be just C. Oops, okay. We need random, of course. So import random, and then we can run this thing. Oh, of course, D is not defined, because instead of D we have Y, right? So this is what we have. Okay, so this is our matrix of coefficients. This is like our y's, and we're looking for x's. Now we call this function called Lindsay solver, and if you actually look at the source, there are two. So they are all in M eigen, and if you look here, they are defined here. So there are actually two solvers. One that is implemented right now is this, and it's just like written from the scratch. And the other one, which is yet to be implemented but will be available soon, is a wrapper one of the existing solvers from eigen. That one will be more efficient. So but the one that we use now is still okay. So it uses some sort of iterative scheme to, well, actually I can show you some code for that matrix being solved. So that's basically a Gauss-Seidel iterative procedure, and you kind of you can look into more details of how that is implemented just here. So and you need to set up some epsilon, the convergence parameter, the maximal number of iterations, because it's an iterative procedure, and that basically gives you the solution. So left hand side is just c times x, and we can print it LHCS. So show matrix, and it is supposed to be equal to the right hand side. So let's do print LHS, print y. Well, actually we already have y, so we'll not be printing it again. And let's see how it works. So this is our y, and this is our left hand side that we were looking to find. Now let's try this procedure with bigger dimensions. So maybe not 3, but let's say how about 10? 10 is not that much, but just I don't want a huge output, so it works in this case pretty nicely. If you have, let's say 100, then we'll see. We'll try to print it out, but of course it will be like difficult to compare. Like this matrix just doesn't make sense to see, and of course it also tells that something has not converged. So in this case I think we can make the convergence a little bit softer, and the way to check it, to check with this all makes sense. So we of course don't want to print these matrices anymore, but we can use we can compute the difference between LHS minus what it is supposed to be, y, right? And we can compute maximum element, that's a magnitude, no, maximal magnitude, and should be very small. So right, let's run it again. Did not converge. Let's try it more iterations, and it still doesn't converge. I don't know. Let's try just 5 maybe. Okay, here it is. So that's what we get. The maximal element of difference is this. Apparently, it's not the most accurate solution. It's needs some sort of and you see sometimes maybe even larger. Oh, okay, I increased the epsilon, so actually I wanted to decrease it. So it still does converge, and perhaps it of course does take more iterations, and remember, every time I run it, we use different sets of random numbers, so it may work from time to time. So we go back to this 10 to the minus 7 and see what happens. Maybe it will converge this time. Doesn't look like that. And we can try to increase the number of iterations. Okay, now it works. It does converge, and you get nice decimal point, so you can get to this accuracy. That's the maximal element of the difference. You can solve this sort of problem quite efficiently, but I think the eigen solver would be even more efficient. Okay, on that, I guess I will finish today's extended tutorial on the various topics of Libra.